Okay, good. Yeah. So yeah, this is the work done with Robert and Hitoshi. And yeah, I will focus on the first one, and I'll just mention the Millicharge experiments briefly in the end. And that is actually connected to the fixed target probe for the dark meson theory as well. So the theme of this talk will be connecting the dark matter to standard model and consider both observation, theory, and experiments. So then we have a complete story about this dark meson theory. And also it will be trying to find the most promising testable dark matter that both can be testable in astrophysics and have some signature in experiments. And yeah, if I'm now hyper worried about the internet connection, so if there's any interruption or things, just let me know right away. I will fix it right away. Okay, good. So here is the outline of the talk. First, I will give a introduction of the resonant self-interacting dark matter. And the interesting thing about this is you can connect these to the small scale structure observations and quantum chromodynamics, mostly meson physics, but of course those are connected to the quantum QCD. And finally, the matter and antimatter asymmetry. And there's also, I will connect from these to the Millicharge particle search and some experiments that I propose. And in general, on this story, it's the probe of the dark sector idea, meaning that in the low mass dark matter scenario, you need various different kind of ingredients or Millicharge, either way. These are just two possibilities. And it would be related to neutrino experiments and neutrino physics. And then I'll give the outlook. So there are certainly deep mysteries that drive us. For this specific talk, it will be what is dark matter mostly. But I will also connect to charge quantization and some neutrino mass and interaction theory very remotely. But mostly I will focus on what is dark matter. And here is Vera Rubin and Paul Dirac, and there's some experiment and observation that related to these mysteries. So first, let's just look at the dark matter. So you've seen this plot 100 times. So just the quick question would be, what do we know actually about the dark matter that is more important than what we already know now? And basically, except some, I would say, anomaly or problems or things like that, we know next to nothing about this dark matter. So this is a empty slides, we know next to nothing. But there's overwhelming observational, astrophysical, and cosmological evidences, which include galactic rotation curve, CMB, and bullet cluster. And today I will talk about the first two, especially the first one, because that will bring us to some hints of the potential dark matter interaction that is beyond gravity. So in principle, we know there is dark matter for various of these. These are mostly for the students that you can look into these. But the only thing that is confirmed right now is that there is gravitational interaction. So anything beyond is not a given. But the first two, either it's galactic rotation curve or CMB, actually hint something about dark matter, which is still on the shaky ground in terms of observation, but still those are some potential evidence. And that's why those may be the place that we can start looking. Okay, so rotation curve, this is the thing that we know very well, so on the outskirts of the galaxy, this is just a illustration, but you can see that on the outskirts of this galaxy, things are moving much faster. And that is because there is a lot of things that is put inside that you cannot see, they are not shining. So if you look at, for example, Messier 33, which is a pretty large galaxy in the local group, then you can see that local group means it's a galaxy group near us, and including the Milky Way galaxy. You can see that there is a big mismatch between the between the measured velocity and the velocity distribution that is supposedly what we observe in terms of considering the visible data. And of course, the way that you can get this visible data is actually to measure measure the thing that are moving, for example, hydrogen. And a homework to student will be that you can relate these V to the dark matter distribution. So for the point mass, for the constant density, the distribution is very different. You can see this 1 power of R, this is inverse 1/2 power of R. So it will give you different distribution. And clearly seen from these, there's a big mismatch between the data and the expected observation and the actual observation. So this clearly shows you there's some dark matter, but we don't know what it is. But that's not where people stop. Now you know there are dark matter. Let's look deeper into something called small scale structure. So you can look into the big scale structure, which is the large scale structure, as they call, which is the cosmological filaments of things that are in the very large scale. And this one is basically consistent with cold dark matter or collisionless dark matter. So there's no problem there. But let's look at small galaxy like dwarf or spiral galaxy, which is 100 light year to 100 kilo light year. So it's small in the cosmological sense. And of course, also galaxy clusters. So this is a little bit bigger scale, but not in the filament scale. This is like one cluster. So this is many, many cluster, the purple one, but the above one is like one cluster. So you can look into it to find out what's the situation for cold dark matter. And once you start looking, you find out there are some problems. So the problem is in quotation marks because recently there's a lot of standard model or astrophysical simulation that better resolve this issue by introducing something called baryonic feedback, which I will tell you very quickly. But let's actually look at these problems first. So there's many complicated problems. Some of these I'm less familiar with, but the easiest one is the core versus cusp, and it's directly connected to what we learned just previously, how we learned about dark matter. So now we learn about dark matter. Let's put dark matter into, for example, a cleaner galaxy called DDO 154. And I was so curious, what is DDO? Sounds like something very cool. But it turns out it's just name. So it's David Dunlap Observatory. And I think this is maybe a Canadian observatory. Okay. So you can actually have these data, and the data can be fitted through a profile that is the core profile. So core just means it's like a core. It's not a sharp thing in the center. But if you put in the amount of dark matter that you expect here, you can use other way to determine the amount of dark matter. It turns out that the simulation is give you a very cuspy profile, meaning that there's a lot here compared to here. So there's a big mismatch. And you can quantify it by this very easy power law. And Sean has a very clear talk that actually goes through a lot of these previous problems that I show you. So that's a very interesting talk. But the easiest one is this one. And there's two major explanations. One is dark matter self-interaction that is quite strongly that can affect things inside. And basically it's thermalize things inside and kind of smoothen the curve. So kind of core the profile, meaning that, yeah, you can have like things bringing out momentum or things like that to core that to, or basically make the profile much smoother. But there's another way, it's called supernova or other processes. So basically supernova or AGN. And supernova is just things that blowing things away. So it's called baryonic feedback because it's first affecting the baryon. You blow the baryon away, and then the baryon affect the gravitational potential, and then affect the distribution. So that's why it's called baryonic feedback. And some of these are successful, some of these are less successful, and it's kind of like a knob you tune. So some people think it's better resolving this issue, some people don't think so. And there's also many other new issues that people find out. So I would say this is still a very active field. So my take on this is you don't look at this as a problem or anomaly, as we say usually, because Usually there's a lot of interesting things think about as anomaly, but this is not quite in the level of the usual particle physics anomaly. I would say this is more like opportunity, because otherwise there's almost no way to find anything beyond gravity for dark matter. This is one of the very few, basically the only one that give you some hints about the dark matter. So this is very interesting from that perspective. So yeah, this may be the one of the very few places. And cluster galaxy provide interesting self-interacting constraints as well, which I will show you. So yeah, my view is that it's the only, maybe one of the only chances to find dark matter effects beyond gravity in the galactic scale. So later on, I will show you some ways to produce dark matter, but those are not really necessary dark matter. Those are just some dark stuff. But here, this is the way to really see the effects of dark matter. And the worst case scenario, it will provide very strong constraint on dark matter self-interaction that is velocity dependent, as I will show you. Okay, so in a bigger scale, there is a huge variety of dark matter, dark sector thing that we search for. And it's great to propose all this kind of thing, but it also means that the chance of any of these being correct is infinitesimal, right? So yeah, we're searching the dark basically. But to me, MEV to GeV has a special place because it's a lot of the thermal dark matter, which I'll touch on in the end. And also there's a lot of anomaly here. So yeah, as I say, I wouldn't say that the small scale structure is a big anomaly, but it's certainly an opportunity and kind of like an anomaly. So that's why it's very interesting to consider things in the MEV to GeV scale. Okay, so small scale structure opportunity, resonant self-interacting dark matter. So the self-interaction has been proposed many years. Spergel and Steinhardt has these dark matter collisions thermalize the particle in the inner halo and smoothen the distribution. And halo profiles are thus related to the velocity average scattering cross-section per dark matter mass. So notice that there is a V inside before you do the average. So it's sigma times V and average, so velocity or ensemble average. So the V is quite important. And then in the dwarf, there's 20 kilometers per second cluster of galaxy. It's much faster. Things are moving much faster because it's a bigger scale. So these are important facts to know. Now, there's a very nice analytical study of the velocity dependent cross-section. And this is very interesting, but let's look into it a little bit deeper to find out how they do it. So first of all, there is a very easy semi-analytical way to do it, that you first calculate the rate. So the rate is this, right? It's the sigma V over M times rho of R1. Okay, I'll tell you what is R1. But that's why when you always look at this self-interaction, you always see sigma V over M. So when I was a student, there was a short period of time I didn't know why it's always sigma V over M, why it's over M. And it's basically just because of the rate. So sigma V over M times rho and times the TH is how many times you scatter. So within a small radius, not a small radius, within a radius R1, you can scatter at least once. And I call this scatter radius, but you can also call it isothermal radius because inside it, things can be thermalized and you can use the isothermal profile to replace it. So inside R1, it's isothermal profile. And outside R1, you can say it's cold dark matter. So you have the cold dark matter distribution. And then once you get that, you map it back to this galaxy. And that's how they get this cross-section. So notice that these are not cross-section, this is cross-section times V basically, and thermal average. So the fixed cross-section is actually going like this. So whenever we show this plot, whenever I show this plot, people will say, yeah, you can fit a horizontal line to these. And that's true. But remember, the horizontal line is corresponding to sigma proportional to 1 over V. So there is already a need for velocity dependence built into this kind of plot. And let me explain the terminology. LSB is low surface brightness spiral galaxy. So it's a small galaxy. So you can see that for different scale, there is different preferred cross-section. Now you can say, but I don't trust this completely. There is a lot of very complicated baryonic feedback things you have to take into account, and that would be true. But this plot at least show you that you cannot have a cross-section much higher than these, so you cannot go here. So these actually give you a kind of a velocity-dependent self-interacting constraint. Yeah. And also, by the way, these two, the dwarf and LSB, are chosen that there is much less baryon inside. So the baryonic feedback effect is much more minimal. In cluster, it's harder, but it's also a larger scale. So dark matter is also important. So I would say these data are already specifically chosen that the baryonic feedbacks are less important. So there's some validity to this, but the baryonic feedback business is very complicated because you can consider the small scale, you can consider the supernova. Larger scale, you consider the active galactic nucleus, meaning the AGN. So there's a lot of complication. So a lot of study are still being done. That's why I say this is an opportunity rather than a strong problem. Yeah. So dark matter self-interaction prefers velocity dependence. Let's get a little bit deeper. So a toy model can be written down that you have a 15 GeV dark matter cell scattering through a light mediator. Sorry, we have some delivery. It's fine. Yeah. So we have a 15 GeV dark matter self-scatter through a 17 MeV kind of mediator. And this is a toy model. So you don't have to, you can think about what kind of model that give you these. But to me, toy model is a toy model. It's not really a attractive thing theoretically. So you can look at things that what could happen in standard model. And in standard model, this will correspond to this cross section. For example, this 1 to 10 centimeters square over G would correspond to the NP scattering, meaning neutron proton elastic scattering. So you can have this hadron scattering, and then you find out that these scattering also have some velocity dependence. So it's very compelling to link these two stories. So the question can be asked, can you model your self-interaction through some hadronic physics? Okay, so that's a segue. So the answer is yes. So that's why we propose this resonance self-interacting dark meson story. And it's a solution to small.
But you the velocity dependent part of that was actually beyond.
Yeah.
So the plot on the left goes only to 5,000, and the other one goes beyond that. And I feel like the velocity dependence is coming for very high velocities.
Yeah. So you're right. So the reason for this velocity, the NP scattering, I haven't thought about how to use that to do this story yet. So this is because there is a pole in the scattering. That's why there is a dependence. But we're not using the NP scattering. We're using other meson. But you're right. The velocity dependence does not match, and you have to do other model building for that. This is just a clear example for the scattering. Yeah, we're not using the NP scattering. This is just to motivate the similarity. Thanks for the question. Okay, yeah. So yeah, we will not use the NP scattering, but we will use other meson. So we'll use the pseudo scalar meson and the vector meson. So, but let's also look at the toy story first, because the toy model is also quite interesting. So the toy model, you can just have a R that is 2 times of the mass of the dark matter with a correction or small difference. And these, you can tune this delta to locate your resonance. This is called resonance self-interacting dark matter. And it's discussed in detail in this paper. Sean and I actually wrote the notes about this, but then Hitoshi published it first, so we didn't publish. But anyway, this is a very interesting structure that you can have. So you can have this intermediate particle that is on resonance and it's on the Bragg-Wigner resonance. So meaning that you have a constant piece and a Bragg-Wigner resonance piece. And the Bragg-Wigner resonance piece is basically matching. So the peak will reach when you match your kinetic energy to the difference between the mass of the 2 times of the dark matter to the resonance mass. So there's a difference between mr minus 2m of the dark matter, which is 2 delta m. And this is why this delta can change your resonance location of the V. And it has to be chosen that the resonance is reached around 100 kilometer per second thermal velocity averaging. So it will be reached here. So that will be the story. And there are some detail of the width and how do we do the velocity averaging. So in the very naive model, you do a very simple one-dimensional kind of velocity averaging. But in reality, you can consider a much more complicated velocity distribution. That's also possible. So there is some, even in this level, there are some improvement that one can do for the thermal velocity averaging. Okay. So now the actual model we do is not the NP scattering. That one may be able to do it, but we have to think harder. The one that we're actually doing is using the B meson and upsilon 4s. So if you look at standard model, actually upsilon 4s is on resonance with B meson. So there is an interesting connection between the two. And if you start to look at the, but first of all, these slides, I just want to show you that now we choose our R to be a vector. But R can also be scalar, which will be a slightly different distribution. And also the delta can also be minus, negative. And the behavior will also be different. So there's a various different model that you can consider. But we found out the vector resonance is the easiest to model based on standard model. So I will get through this route. But the scalar resonance is also interesting, and we're starting to think about it in the standard model. Okay. So furthermore, but of course I will not use actual standard model because we know this is not dark matter, but we'll use some analogy. But the thing is, once you start looking, you find out there is everywhere. There's a lot of resonance structure. So the K meson is also about half of the phi meson. B meson is about half the upsilon 4s meson. And then we just decided to do a standard model figure. So this figure is completely made of standard model. So it's a great thing that I feel good that I organized the standard model measurement in an interesting way. So maybe we can, yeah, it's a good thing. Anyway, so there is vector resonance and the pseudo scalar meson mass. So let me explain these plots a little bit more. So y-axis is the meson mass, and this is the 2 times of the pseudo scalar meson mass, meaning that pion, kaon, B meson, D meson, and B meson. This corresponding to the D quark, S quark, C quark, and B quark. So all the quarks. So basically all the interesting quarks are here except the T, but T because T decay, because it opens up other decay channels. So, but in an ideal world that the TD bar does not decay, things will also be similar. Not the TD bar, sorry, the heavy T and light quark meson. If that doesn't decay so fast, that will also be on the plot. So these are the vector first level, second level, third level. So for the students, this V 1s, 2s, 3s meaning that you have excited state, because these are basically quarkonium, and you can think about this as the electron positron, but a strongly interacting one. So the quarkonium can also have first state, second state, third state, and then you find out that these PS will cross and have the resonance in various different locations. So it's very interesting. Actually, you have 3 resonance structure here. Okay, so that's very interesting. And if you look furthermore, there's a lot more resonance structure, and one of these is a very understood one. So this one is very understood. Not understood, sorry. This one is very well discussed through the anthropic principle, actually, because these process, these kind of carbon related to beryllium and alpha, this process is necessary. The number has to be so small that the astrophysical process will go through properly. So if this number is changed, then we will not be here. So there is an anthropic principle to fix this number. So this is very interesting. There are also other ones that we found that are not necessarily have any clear explanation. So we put them here. So some of these might have some better explanation, but we don't know. But there's just a lot of resonance. And maybe there's some conspiracy behind all these by some non-theoretical motivation, but we haven't thought about, we haven't figured out what it is, other than this one that has anthropic principle explanation. Okay, so let's further do some model building. Let's build a kind of semi-coincidence situation. So the easiest one to think about would be the kaon, but the kaon is also kind of like a pion. So let me explain this a little bit. So I use K prime. So K prime is now my dark matter, and K is made of S and U bar, or S bar U dark quark. So I will analogous this K prime to standard model K, go through some phi prime and come back to K plus K minus. And then I can get this resonance structure. But notice that if I build this model, there's also 4 kaon interaction. So the 4 kaon interaction will actually set the constant piece. So that is something to worry about because that could set a constraint, as I will show you later. But then the dark matter will be roughly go to GeV to get this kind of resonance behavior. And we also, this one we also cannot calculate. So we fix the phi prime K plus K minus to this to get some parameter. Okay, so here is the detailed model building. So the model building is quite easy. You just have 2 quark. One is S quark, one is U quark, and both are below the dark lambda QCD. So here I drop all the prime because there's too many prime, it's annoying. So everything is DM here. And then eventually you have your quark, you have your kaon spectrum and 4 kaon interaction. In its 2 flavor, U mass much smaller than S mass, but they are both smaller than lambda QCD in the dark sector.
Why haven't you been you haven't been including pions very much, except sort of mentioning them in passing, and
right,
they would be dominant in low energy scattering.
Yeah, but these are pion in my story actually because I don't have the D. So
okay, so you only have like a 1 light quark plus the S quark.
That's right. That's right. Yeah.
Okay.
So, sort of a confusing naming, but this is to capture the situation that you have.
No.
Yeah.
Okay.
Yeah.
Thanks.
Yeah. Thanks for the comment. Yeah. So yeah. So these, if you are thinking about the actual, in terms of spectrum, these are more like a pion story because there's only 2 quarks. So you have this kind of pion-like theory, but we call it kaon because the mass hierarchy. And then this kaon or pion stuff can scatter through different ways through 4 kaon interaction or kaon resonance situation. So actually these 2 processes fix the preferred parameter to different location. So if you fix the standard model to be fix the standard model for kaon based on the fit to this figure, it will point you to this lower mass situation. And if you fix the 4 kaon, but sorry, not 4 kaon, kaons to resonance situation, it will bring you to about 1 GeV. So both regime are interesting because you can imagine you change one of these slightly, so then the 2 regime will merge. But if you just directly fix by the standard model coupling strength, then this is what you get. So it's not perfect, but it's fine. And now you can start to change your standard model gauge, so not the dark sector gauge group to see if you can merge them closer. So we didn't do that because we just want to have a out of the box kind of model to show the interesting thing about this scenario. So these are the scenario, and I will explain to you what this plot is. So everything this point to is just the mass to give you the resonance, but you also still want to have the right radical abundance. So yeah, we don't just want to do the dark sector thing. We also want to have a freeze out. So we freeze out through also a very standard scenario that you have K plus, K minus going through dark photon, going to standard model particle. And the dark photon is the quintessential dark photon that you have mixing with standard model photon. And now you can play with the different mass. So the dark photon is heavier than the standard model in the kaon in this scenario. And this is the mass. Sorry, I clicked the wrong thing. So this is quantifying the mass. So the dark photon mass actually also needs to be quite on resonance to avoid the bound, because if it's not on resonance, it will already be ruled out by a lot of this direct detection, like DM nucleon scattering or DM electron. So there's also a mild resonance that we introduce in the dark photon sector. So I would say that this model is not the perfect one. It's okay. It has its feature and it's tell you the interesting stuff about the dark sector, but it's not perfect. But it has signature, so it's both good and bad. You can give and take. These are the out of the box model if you want to build a light kaon or light quark story. So this is it.
Can I ask a question about a couple questions?
Yeah.
So what is the electric charge of the strange quark and the up quark? And is it the same as in the standard model? So
yeah,
1/3 or something like that.
So the strange quark, you have so basically, I should come to I think we specify here. Yeah, good. So the strange, so just for convenience, we put the S quark to be chargeless and the U quark to be +1, right? So we actually don't want, this is the quark, the charge that we specify under this U1. So it's not completely the same as the standard model. Yeah, for simplicity, for sure. And one thing to be a little bit cautious about is once you introduce this charge, you automatically have to worry about the diagram that you have K plus K minus go through AD and K plus K minus, but the T channel diagram.
Yep.
So so that one we have to check, and that one is small in this case, so that one is fine. But once you introduce that, you have to also check that. Yeah.
Okay.
So, yeah.
And there should also be a neutral kaon, right? Does that play any role in the story?
Yes, exactly. You're right. So neutral kaon supposedly could be a dark matter, but there is something called I think I specify somewhere, maybe
Chiral anomaly, I guess, right?
Yeah, maybe I removed it. Okay, so there is a story. Okay, sorry, I should add it back. So this is prepared for the simpler talk, so I didn't get into that deep. Okay, so you're right. The neutral kaon can be dark matter, and you can take two routes. You can say that it's basically the same mass as the dark matter, but there could be some problem because the neutral kaon may decay or may annihilate away or things like that. So you need to actually worry about that. So the easy way out is you say there is a L7 term in the chiral Lagrangian. And if you turn the L7 up, you will make your neutral kaon to be heavier than your K plus K minus. So eventually the neutral kaon will not be the dark matter because the K0 will annihilate it into K plus K minus.
Yeah.
So the neutral kaon will not have current radical abundance now. Yeah.
I have a question. You have this dark photon that mixes with the standard model photon.
Yep.
So there must be limits on some of the dark matter particles from just standard, very rare standard model vector meson decays.
Yes. Those have to be taken into account. and that would be the constraint on the dark photon parameter. But for this dark photon parameter, it's not yet constrained. The strongest constraint is from Bell, I think, the missing energy surge. Yeah, missing energy or missing momentum surge. Yeah, but you're right. Those will come into play. Yeah. Yeah, I would say it's an invisible decay. Yeah. Your dark photon will you'll introduce some. Yeah, you're right. So you can have a vector meson and going through a virtual photon, but mixed with the AD and decay. And yeah, that will affect your decay, but that's not the strongest constraint in this parameter. The strongest constraint in this parameter are for the dark photon itself is the invisible surge in Bell, or yeah, in these electron machines. There are other questions? Okay, yeah, we can chat about this a little bit more. I have another better model, I would say. Depends on how you think about it. I think it's much better. So there is a different model, which is a asymmetric resonant dark meson. And I'm happy to chat about all the detail of this model because this model can be further improved. We just checked it's fine, but it can be better. So I want to say the asymmetric resonant dark meson story. So now we understand the K-on can do it, but how about B meson? And actually B meson is more nature to give you a resonance. And I'll get into the detail. So let's look at the standard model stuff, okay? So the standard model, this process is possible, but you never see it because you have to scatter B meson before it decay, and you have to have the this kind of B meson that is anti-B meson to produce. But anyway, you have a B meson is a bound state of B, D, and B is the heavy one, and D is the light one. And NB is much larger than lambda QCD, the QCD scale parameter. And option 4S is the fourth excited quarkonium state. Okay, so that's the setup. And then we want to make an analogy of that. So now you can look at this. This is a paper from Chris Crick and John Rosner from 44 years ago. So we directly use this to model our dark matter. And they are both in the Chicago land, so I learned a lot from them. This is kind of very nice to connect their study to our study. And so first here, I want to define something called close to the resonance-ness, meaning that how easy are you to hit the resonance? Because previously you hit the resonance kind of by accident. But here I want to be very easy or naturally to hit the resonance. Because if you're working with Satoshi, you want things to be nature. So this is the model that can be more nature than that one. So the delta N is, again, the splitting in the level. Not again, sorry, this is the first time I said this. So delta N is the mass splitting. MQ is the quark of the mass of the quark, the heavy quark. And then you can change your MQ over lambda to go on this curve. But notice that MQ over lambda first have to be much larger than 1. That we kind of understand because this is a heavy quark. But not only that, but also you want it to be quite large. And we quantify how easy you hit the resonance by, yeah, sorry. A question?
Sorry, that was my cat rocking across the keyboard.
Yeah, no problem. Yeah, so you can say that how easy can I hit the resonance is I go on this MQ thing and I define a dimensionless parameter to say, okay, this is how easy I can hit the resonance. The smaller this number is, the better I can hit the resonance. So that's the best we can do. And we want our MQ prime over lambda prime to be larger than 20 to go on the N states. And N will be basically defined by MQ. So a comment I want to make is, of course, all the resonance state, not all the resonance, all the states can contribute in the scattering process, but only the closest one will provide the breadwinner resonance. And that is the one that we pick out. And if you want your N to be 10, if you go to N to be 10, then it will be very easy to hit the resonance. And that requires you to go to MQ prime over lambda prime to be larger than 20. Okay, so that's the setup. So now we build a asymmetric model. So B prime and D prime abundance are set by the asymmetry, and this is how you fix the dependence abundance. And for simplicity, we make C prime, B prime quark to be the same mass. So in your spectrum, now you have a different spectrum. You have a B prime spectrum, you have a D prime meson, D prime meson. Mass of the B prime is about the same as mass of D prime, much heavier than the lambda, QCD dark, much heavier than the pion. So now you do have pion, and you have to worry about the pion. And now you have a B prime, D prime scattering to upsilon NS. And the N is again decided by how large your MQ is. So we want the N to be as large as possible and MQ to be as large as possible. Okay, so that's the setup. And why do you need asymmetry? Is because if this is if you don't have B and D to be different, if you just have B and B prime, then okay, B bar. If you just have B and anti-B, then they will annihilate into pion, and you will not have this very nice story. So you really need the asymmetry. But asymmetry is also good because asymmetry just directly sets your dark matter mass in the simplest way. So this slide is prepared for the student. So asymmetric dark matter just means that you have more dark matter than anti-dark matter, similar to our world that has more matter than antimatter. And the symmetric part, meaning the part that you have the same abundance, will basically annihilate away. So if you assume same origin, the number density of dark matter is the same as number density of the standard model closely. So the dark matter mass will just be 5 times of the proton mass, because there's 5 times more dark matter than standard model particle. So it will be 5 GeV. So that's how we fix the dark matter mass. And once you fix the dark matter mass, everything is basically fixed. You fix the dark matter mass, you want your MQ prime over lambda to be about 20. And then you determine by these fits that the coupling you need is about 27 dimensionless coupling. So B prime, D prime, upsilon 10s has to be about 27. And it's actually very close to the standard model BB upsilon 4s coupling. So this to me is quite a success, because even though you cannot calculate it, the one you need is basically the same as standard model mass. So it means that the analogy to standard model is very good. And you can now do a lattice QCD, and we're chatting with the lattice QCD people that they might be able to do it. Maybe, yeah. And people are actually doing that, as I will show you an example in the end. So now you can ask what happened to the dark pion. Okay, so the dark pion will have to decay. So you can have many ways for the dark pion to decay, but the easiest way to have even a signature that is interesting is to have the dark pion to decay to dark photon, and again this dark photon decays to lepton pair. But this is different from the previous dark photon, because this dark photon is lighter than your dark pion. So you want this to decay. And now you fix your mass of the dark matter, and you also push down your lambda QCD. And your lambda QCD is about the same as your pion mass. It's larger than 2 times of the dark photon mass. So now you see an interesting phenomenology, because the lower the mass of the dark photon is, the more likely one hits the resonance. So I will show you this phenomenology. But just, yeah, this is the dark photon theory that I introduced. And this is also for the students. The dark photon is kind of kinetic mixing. This term is introduced from high energy. And there is a theorem called Lee-Weinberg theorem saying that if you want your dark matter to freeze out properly, and your dark matter is a light dark matter, that's say GeV, then you need an additional mediator other than weak interaction bosons. So you need something like dark photon, or you can use your actual photon to freeze out, and that will bring you to the Millicharge dark matter. So these are the 2 scenarios. You either need the dark sector to freeze out, or you need Millicharge dark matter. So that's how the 2 talk links, two sides of the story links. But this is a side way. And now you can search for this dark photon in one of the experiments that I proposed. So in this something called Sequest, this is an experiment called Sequest. Now it's renamed to be DarkQuest, is to study the C-quark scattering. But now there is an idea proposed by the Kentucky group and the SLAC group that you can remove this wall and put a EM-cal here to search for dark photon. So if you're familiar with, let's say, Codex B, this is kind of similar, although in a different machine. But now what I propose is, I think this is not the optimal situation because you have to remove the wall and you also have to interfere the operation. The most easy way is to put a detector behind this iron block here to search for lonely particle. And it's very nice, very clean. There's no need to remove anything, so it's low cost. And you also not mess up this very nice nuclear measurement. So that would be my proposal. And we're writing a more detailed paper, but we have the concept in this paper now. Yeah, so it will be much lower background, low cost, not interfering with quark study. But the original idea is very clever and very nice. We just think that there is a slightly convenient way to do it. Okay, so finally, let me bring you to a dark photon phenomenology. So now you have this quantification of how easy you hit your resonance. And the further you push down your dark photon mass, the easier you can hit the resonance. So this is 10 to the minus 2, 10 to the 3, 10 to the minus 4. Because your dark matter mass is fixed, you fix your quark mass, you need your splitting between MQ and lambda. So this push down your lambda. And lambda QCD is about the same as pion mass and has to be larger than the dark photon mass. So the dark photon mass around 100 MeV is preferred. So this is the interesting parameter. And there's many experiments to search for this. And one of those is the LongQuest experiment that I proposed. And the kinetic mixing is around this region. Okay. So that's the story. Is there any question? I can answer those in the end. Let me just quickly mention this one that does not work. So this story is very nice. Let me just show you one last thing. So this story is very nice. It's a complete story, but it leads us to also think about how about those previous model that we built, those previous model that Hitoshi and I consider for other purposes. So previously we consider this strongly interacting dark matter that the freeze out is through number changing process. So this is called SIMP and elder. Depends on if you freeze out first or decouple first. If you freeze out first, then it's SIMP. If you decouple first, then it's elder because it's elder decoupling. But both need some kind of 5-pion interaction. So sorry, this plot is blocking some text, but basically everything, yeah. So you need some 5-pion interaction. So there is a very attractive model proposed in this paper that it's the 5-pion interaction Wess-Zumino-Witten term. So if you specify your gauge group, your fermion number, and everything, you got a very attractive 5-pion interaction. And this 5-pion interaction can be your freeze-out process, basically. So that's everything is good. And we can get into the detail if we want, but that's the story. But the interesting thing is people actually did a lattice QCD study. So you actually know where you can find a vector resonance because they actually did it. They actually use the exact same model. I think it's motivated by this paper to actually do the lattice QCD study and actually find there is a resonance. So if you fix your parameter, m pi over f pi to be 1.9, you actually do have a vector resonance that can give you the resonance structure. So everything is good because you have 3-to-2 freeze out, you have a resonance structure, but in the end, it doesn't work because the 4-pion interaction is too strong. So when you introduce the Wess-Zumino-Witten term, yeah, you fix your 5-pion, but naturally in your story, you also have the 4-pion interaction. And the 4-pion interaction actually give you a too strong of a self-interacting scatter. So it actually got ruled out in the end. So the story is very nice, but it doesn't work in the end. but we still present it because it's the example that the constraint is very strong. So let me summarize. This is a general scenario to naturally give the resonance structure, has interesting structure similar to standard model QCD, can easily connect to lattice dark QCD study, has signature that can be searched for in experiments and testable in astrophysical study. In what sense? In the sense that if you understand the more data here, then you can distinguish between various different models. Either it's the scalar resonance or the vector resonance. And among vector resonance, there's also different kind of constant velocity piece that you can rule out. And actually, there's a recent paper by Hayashi et al. That they find out that actually the resonance one could be more preferable than these other one, because they find out that the galaxy here prefer a very, very small cross section. But some of my collaborator doesn't completely agree with that paper, so I didn't show you that figure. So we are actually also doing this to look into this data better to see what's the actual story here. And as I say, things here are getting messier and messier once you consider all the things that could happen in the galaxy, which is a lot. So I would say this will still take quite a long time to understand the actual structure, but it's a very interesting study. Okay, so it's a good segue. So is there any question? Let me see how much time do I. Sorry. Yeah, please ask any question. Oh.
Yeah, can I ask you a question?
Yeah.
I mean, maybe you can't answer this, but you talked about like baryonic uncertainties in the galaxies. How much should these error bars be trusted? And if they shouldn't be trusted, shouldn't the experimental or the observational, the people doing those astrophysical observations actually like put error bars that accurately capture the uncertainty?
Yeah, I completely agree. Yeah, I think that's a great, actually, I would say that's a more of a very nice statement, that the error bar should be much larger. So a lot of the model that I say are ruled out. If you enlarge the error bar, then might still fit. And you're right that so these error bar are basically decided using the semi-analytical measurement. Sorry, not measurement. The semi-analytical process that I described previously. So those certainly doesn't take into account simulation or baryonic feedback, although they do try to find out a cleaner galaxy to do this. This is still not a proper quantification of the error bar. So you're right that the actual error bar should be much larger. And that's something that can be done properly. But for the kind of the interest of the talk today, we are just going with the simplest model building, the motivated.
Yeah, totally. I mean, just as sort of I mean, those things can be very political too, and
yeah, I would say to me it's
something
not so political from my point of view, because to me a model is, you can think about these two ways. One is this actually interesting or not? Is there a nice model to describe it? And there yes. But secondly, model is a way to quantify, to parameterize basically your measurement. Because if there is no good model, then you cannot quantify what kind of shape you expect. So a reverse way to do this is actually the following, which I think is more interesting from my perspective. That is, you use your predicted dark matter self-interaction, depending on the velocity, to try to generate the galaxy profile in different situations. Right? That is more difficult, but that's possible to do. So basically,
because you have a velocity distribution, like the average velocity, it depends on the, you need to know how you're weighting that average, I guess, maybe.
Yeah. So the idea is this: for each galaxy, you have some kind of preferred velocity. You plug that in, you do the velocity average, and then you throw in whatever state-of-the-art baryonic
convolve it properly.
And then eventually you get your actual how the galaxy look like, and then you match to your data. So that would be the most proper way to do it. but that certainly takes a lot of computation and things like that. So we need quantum computing. We can quantum computing.
Fair enough. Fair enough. Sorry about the derail.
No, that's a good discussion. And I will actually just spend a few minutes for the final thing that I want to mention. So the final thing I want to mention is a complete segue, but in some spirits, it's very related to the dark photon search. And it's actually a different angle of the dark photon search. That is to search for scattering. And the thing that actually scatter is the Millicharge particle. So as I say, there's many motivations for Millicharge particle. Some of these include the Millicharge particle can be related to massless dark photon. So the previous dark photon story, but make it massless. And it's independently interesting if you don't assume it to be dark matter, but it could be a dark matter candidate. And it can be think about as interesting as the fractional quantum Hall effect. So basically, Millicharge particle is just something with a small hypercharge. And in standard model, all the hypercharge are fixed. But if you have an extra particle, the hypercharge can be very small. And it's weird that we don't find it. So actually, there's a lot of effort in the past that try to find it. And recently, you can also use that to explain the edges result. If you're interested, I can tell you that. And that is related to the CMB, because the edges measurement is measuring the CMB when CMB passed through this gas and got absorbed. So there's a 21 centimeter measurement of the absorption, and they found the absorption is much stronger than what it should be. So the idea is that if you have some Millicharge dark matter, it will affect absorption. So that's the story. But the Millicharge particle model is extremely simple. You just literally have something with a very small hypercharge. And this term is completely legal. As I always like to say, you will not get into jail, even if you're in Germany, it's totally fine. It's totally legal. Nobody can say you're not legal. But it's also not morally correct. So you have this dark photon to couple to your photon to give you this kind of Millicharge story by Hodem. So this is the story of Millicharge. But today we will just search for something literally with a very small electric charge. And the Z coupling is also there, but it's suppressed in the low energy. So you have two ways to search for it. One is your Millicharge after produced in the PP collision or particle nucleon collision. These things can scatter with electron, and you can see them in the neutrino experiment, for example, because neutrino experiment can see electron scatter. Or you can scintillate things. So because Millicharge is kind of like an electron with a small charge. So you can also use scintillation experiment to search for it. And this is a very nice design designed by Millikan to do that. And recently, since you have to do machine learning to survive, now I'm learning machine learning to do this in the Neutrino Detector. And this is a very exciting new project that I'm doing with Argon New and Doom people. I actually just initiated last week that you can identify very faint track in these detectors. So you have an A, B, and B prime way to search for them. And now once you understand this, you can apply it everywhere. So the first thing we apply is exactly the neutrino experiment in Dune. And you can calculate the different kind of production channel I listed here. And then they can fly into a Dune detector to search for it. Secondly, you can use the same thing as the Millikan, put it in downstream of the proton fixed target machine to search for Millicharge particle. I call it Fermini because it's for Millicharge particle at Fermilab. So you can search for it. And thirdly, you can go through the forward regime. I call this Formosa because it's a forward microcharge search that you can do it in the same location as the phaser and other experiment to search for Millicharge particle. And finally, you can also produce this Millicharge particle through cosmic ray production. So you have cosmic ray hitting your atmosphere, Millicharge particle coming out, hit the neutrino observatory, and you can search for them. So I'm happy to chat about all of these. Some of these are more solid than the other one, but these are all very interesting. And now you can have a compilation of all the different kind of experiment to search for things in this parameter. And yeah, so these are different. So you have neutrino experiment, super K from the cosmic production, Fermini and Formosa, and these are different search. And yeah, these are some detail. And finally, this is the thing I mentioned. Why is this parameter interesting? It's because this parameter is directly linked to the edges anomaly. So edges anomaly, as I say in words, you have CMB going through hydrogen, and the absorption is measured by edges. And edges, there's still a huge debate about how reliable this result is. But I would say, again, look at this reversely. This also, again, is one of the very few situations that you can actually understand dark matter interaction beyond gravity. And a stronger statement I would make is the reverse statement. I would say that if a small portion of your dark matter is millicharge, then you will affect this CMB measurement strongly. Either it's the actual CMB, the Planck measurement, or the edges measurement, because slightly dark matter being millicharge will affect all these measurements. So I would say reversely, that is more interesting. Directly motivated by this experiment to say dark matter is millicharged, it's very shaky, but we can still think about this. So if you really think that millicharge particle, you use that to explain this. If you have the normal millicharge particle by itself, this is the parameter that can do that. But if you also allow some model building, you can expand the parameter to be much larger. And this is exactly the interesting parameter that we can probe in fixed target experiments or collider experiment or anything proton colliding with proton. So that's the interesting place. And finally, this is also the strongly interacting millicharge dark matter regime, meaning that when you have dark matter that is millicharged coming into your atmosphere, it will get stuck. So you will never reach the underground detector. And this regime is where the fixed target or accelerator experiments are the most powerful because they don't care. They just produce this millicharge dark matter particle, and then you can see them in the detector. So these also show you the complementarity of different experiments. You can have accelerator that probe the strongly interacting regime, and you can have the direct detection to probe the other regime and kind of close out this interesting millicharge strongly interacting dark matter window together. Yeah. Oh, so I'm ending the talk. So finally, you can also do neutrino experiment in the forward regime. And Phaser New has done a lot of these. I'm not in the Phaser New or Phaser collaboration, but I joined the forward physics facility discussion that maybe you can propose a lot of experiments here. And one of the rather interesting proposal I think I suggested is that maybe we can put the proto-dune further downstream of even the phaser regime. So find an open regime here to put your proto-dune there to search for neutrino physics. And that will be very interesting because there will be some regime that is not previously studied properly. And this is a plot from the Phaser New that I'm not involved with, but maybe you can help fill up a gap here. Okay, so this is a summary of the research program that I do a lot of this model building. And I also propose new experiment to search for dark sector, including dark photon, millicharge particle, or many other 100 different kind of model. And we can develop also new cosmology or astrophysics study. They are complementary. For example, dark matter in neutron star, or is GW17, OA17 a primordial black hole events, this kind of thing. And I list them here in case you're interested in chatting about them. But I will not say anything more about this. Yeah, thank you. Thanks a lot.
Thank you, Yudai. Thanks so much for the talk and for the discussion that it generated. Do we have any further questions?
Let me post